Okay, hi everyone. Thank you very much to the organizing for giving me this opportunity to share with you the latest result from our flashlight survey. The aim of this survey, I'm going to just say it in a few words, is to do direct imaging of the cosmic web using a quasar-induced Lyman alpha emission. And it's basically summarized in these cover slides. You can probably recognize this is the cosmic web, that's a simulation, but what you see at the center of the simulation is actually a real image that we took with Keck recently, and that's been featured in Nature recently. And many of my collaborators are actually in this room or in Santa Cruz today. So, but since this is the first talk about intergalactic medium of this Galaxy workshop, I just want to spend one slide to sort of motivate why studying the intergalactic medium is interesting. And that's one of the reasons that for me the intergalactic medium is very interesting to study, because it provides the link between the bright part of the universe that we can see with the HST optical telescope and the dark side of the universe that we can actually get in our simulation. So if you want to understand how to go from this picture to this picture and vice versa, you have to know you have to know the physics and the evolution of the intergalactic medium. And so today I'm going to focus on three particular scales and three particular questions on the intergalactic medium, starting from the smaller scales associated with the densest knots, with the densest clumps into the IgM. So the question which I'd like to know is, how is gas converted into stars? Is there a dark galaxy phase, a phase in which you have a lot of gas and very little star formation? On a 200 kiloparsec scale, we'd like to know how do galaxies get their gas? So the circumgalactic medium physics. Is the circumgalactic medium cold, hot, whatever temperature it has? And on larger scales, we would like to know how do galaxies are linked to each other, what the morphology and the small scale properties of the cosmic web. And in the next 15 minutes, I'm trying to answer these questions if I have time. So the classical approach to study the IgM is in absorption, and we heard a nice talk by Ryan this morning. It's a very powerful method. You get a lot of information about low density gas, including metals, but it has one drawback. Drawback, that is, you only get one-dimensional information on the system you detect. So you get 1D information on Lambda limit system and DLAs, and sometimes it's difficult to argue that a DLA may be a filament, a galaxy, whatever it is. If you really would like to understand the system, you need direct imaging. And my favorite solution to do direct imaging is to use fluorescent Lyman alpha emission. Fluorescent Lyman alpha emission is produced by H1 clouds that are illuminated by an external source, like a quasar or a galaxy. What happens is that the part of the gas is ionized, it recombines, and it produces Lyman alpha emission following recombination. So in this case, you can actually detect these objects even if there is no star formation within them, and you can get two-dimensional information. You can maybe not read this from the bottom there. Just want to say that if the gas is fully ionized, the Lyman alpha emission is proportional to the density square. So you get information on the density of these systems. So I spent a large part of my career trying to model and understand how bright is fluorescent Lyman alpha emission. I'm just going to give you here an example from a recent simulation. What we do is to run cosmological hadron simulation, Ramses especially, and then post-processing them with a 3D radio transfer code that I wrote, Radamesh, for ionizing and Lyman alpha radiation. And this is a 10 megaparsec zoom-in region centered on a massive halo, and this is the H column density. And now what we do, we apply our radio transfer code to produce simulated Lyman alpha images. As you can see from this image here, when we include the UV background and stars, you can actually see the cosmic web, the structure there. But there is a problem. And the problem is that the surface brightness that you expect is 10 to the minus 20. So this thing is completely invisible with current facilities, unless you give me 1,000 hours of BLT or Keck time. But since that's not the case, we have to find a trick to make the cosmic web visible with our current facilities. And our favorite trick is to turn a quasar at the center of this box here, and the quasar is going to make the densest part of the cosmic web hundreds of times brighter. So 10 to the minus 18, something that you can detect now. Of course, most of the web that is low density will stay at the same level, but the densest part of the cosmic web will become visible at the level that is currently feasible with our facilities. So how can we observe then? First of all, we have to look around the black quasar, as I said, and what we use is deep narrowband imaging and continuum to constrain the Lyman alpha properties and the continuum of any galaxy that is there in order to remove those kind of foregrounds in our survey. We were lucky enough to get time for a pilot survey at the VLT when I was still a postdoc in Cambridge. We use a custom-built filter. It was specifically designed for one of the brightest quasars, Redshift 2.4, and we took one of the deepest narrowband image ever taken at the VLT, 21 hours, you can see it here, and also a very deep continuum image at the same time. And then we use the usual narrowband access technique to select Lyman alpha objects around the quasar, Redshift 2.4. And we detect about 100 Lyman alpha sources around the quasar that are indicated by these little circles there. And 30 of them don't show any continuum. And we believe that among those sources, there are candidates that are dark galaxies of cosmic gas, because there is no continuum from stars. How can we actually distinguish dark galaxies from normal galaxies in this field? The way in which we do that, we look at the equivalent width of the line, of the Lyman alpha line, because there's a well-known theoretical prediction for which galaxies cannot produce more than a few hundred angstrom of equivalent width, because whenever you have Lyman alpha, you also have continuum from stars. These objects here are the one with no continuum detection, so we only have a lower limit on the equivalent width, and 12 of them are well above the line, the limit for galaxies. And our equivalent width distribution, that is this solid histogram, shows a much larger fraction of high equivalent width object with respect to blank surveys here. That is telling us that the quasar is doing something at this field and that is illuminating the gas for us. So how do they look like? Finally, I can show you an image of the dark galaxy. Here they are, little dots, not very exciting, but were very exciting for us because we were looking for them since a very long time. Here you see postage stamp images of the dark galaxies, of the gas illuminated by the quasar, and of the stars that are not there. You see no detection in the continuum. Even if we do a stack of all of them, we don't see anything in the continuum at all. We don't see any extended emission in Lyman alpha. It's probably telling us that these objects are very compact, so they are compatible to be very small proto-galaxies or very small dark galaxy, actually dwarf galaxy, we can say them, like Ryan showed this morning, but we know star formation in them. And the Lyman alpha, I want to stress, is coming from the illumination provided by the quasar that is megaparsec away from these sources. So we got 22 orbits of HST this cycle to constrain their sizes, so and try to understand how large these things are. What we can do with them, we detect them, but we can also constrain the physics of this early phases of galaxy formation. How? Well, the Lyman alpha emission depends on the density square, as I said. So the Lyman alpha luminosity is related to the gas mass. We can do it analytically or using full radio transfer simulation, that is these dots here. The results agree and are telling us that given the large Lyman alpha luminosity, the gas mass of this thing needs to be 10 to the 9 solar masses. So there is a lot of gas sitting there and not forming stars. Actually, how much stars are they forming? Well, from the stack, we can constrain the star formation rate, that's to be less than this value. It gives us a gas consumption time of 100 giga-year or larger. This means Redshift 2.4, a lot of gas sitting there, not forming stars, at the peak of the star formation history of the universe. Where are they of the Koenig-Schmidt relation? We can do this exercise, taking the upper limits on the size. That's the classical sequence in the Koenig-Schmidt relation. This is where our data is. If you cannot say it, I'm going to point it here, the people at the back. Far away from the Redshift 2 galaxies, but also from local galaxies. But actually consistent with recent theoretical modeling that were suggesting that low mass galaxy, high redshift with low metallicity will have very low star formation efficiencies. And with this method, we can actually constrain this early phases of galaxy formation. Let me move now to the second topic. You also saw in this plot here, there are some objects with continuum detection that are above this line. What they are? Well, the quasar is shining on any gas that is there. So it's not only shining on dark galaxies, but also on the circumgalactic medium on normal galaxies. And indeed, this object here are objects with extended emission. One of them may be like a merger, but in this one here, I'm going to show now a zoom of this, the continuum subtracted narrowband image. shows filamentary distribution of gas around it with the scale and morphology compatible with the infamous cold streams, but also with Tadra streams. And I want to stress the quasar is 3 Archimedes away from here, so that thing is very far away from the quasar. We got recently a 2D spectrum of this object, so I'm showing the spectrum in this direction here. The spectral shape is it's double-peaked and compatible with cold, optically thick gas illuminated by the quasar. And also the kinematics seems to suggest that this is indeed just cold silicon-galactic medium around this galaxy. And we're going to do a more detailed comparison with Lyman alpha radiation transfer simulation in the future. So after the success of the pilot survey, we decided here in Santa Cruz to build a much larger sample of quasar-induced Lyman alpha emission, and we built the flashlight survey. The target were 20 bright SDSS quasar redshift 2 with custom-built filters using Keck and Gemini. Unfortunately, 50% of our time was weathered out on Keck the last 2 years. But still, we were able to get at least 6 quasars and from Keck and 3 and actually 13 from Gemini. I'm going to show you now the first result from this survey. This is actually the result from my first night at Keck. I was sitting there at the telescope and waiting for the image to arrive. You know, if you want to detect this dark galaxy, it's going to take a longer time. You have to integrate things. Usually, you don't see much if you're an observer at the first exposure, unless you're looking at something very bright. So I was very surprised then when I saw this. You see here the narrowband image on the left and the continuum image on the right. Here's the quasar. And around the quasar, there is a huge nebula of about 1 Archimedes on site that was completely unexpected to us, given our previous result. Just want to stress there is nothing in the continuum in correspondence of that nebula there that is telling us that it's actually Lyman alpha emission at the redshift of the quasar. So this is a continuous subtracted narrowband image. Now you're looking at the Lyman alpha from this object there. You can see actually there are 2 objects. A is the main target quasar, but we discovered another fainter quasar here, B. And the Lyman alpha nebula is actually pointing towards this direction there. I just want to stress that the size of this thing is 500 physical kiloparsec. So this extends to well beyond the virial radius of this object. And there is nothing, and this is at least 3 times as large as the classical Lyman alpha blobs that were discovered before. So there is nothing compared to that was discovered before. And this is around a radio-quiet quasar. So we believe this is the first detection of an intragalactic filament, given its size. Nebula usually have a name. So I was sitting in front of the computer trying to find a name for these objects and for this nebula. And you know, I live in Santa Cruz, and most of the local people already recognize that this thing has a shape very familiar to you. Well, of course, it's the Lyman alpha slug, and that's the reason why this nebula has been called the slug nebula. You see here, that's the tail and the thing, and that's my collaborator there waving at you. I think it's X. Unfortunately, Nature editor didn't like the name. So in the Nature paper, you will find the telephone number of this thing. But locally, it's known as a slug nebula. As a very good slug, it's very quiet and very slow. We took a 2D spectrum recently of this object, so put a slit here. The spectrum also looks really amazing. It's 200 kiloparsec, extremely narrow and collimated, spatially coherent Lyman alpha emission. So it's a kinematically quiet nebula. It's not an outflow, it's not a crazy thing. It's just a slug sitting there. And we would like to get high resolution spectroscopy, but we've been weathered out twice. So let's hope we can get this in the future. Quickly, then we moved in the same night we moved to the second object, and there was another quasar. We know already there was some extended emission around it from spectroscopy, but we were also unprepared about the result of the second target. When we were sitting there after the first object, we detect this. Another huge nebula, actually the second largest Lyman alpha nebula ever discovered. And you may notice here, that was the same night of Keck. It was my first night of Keck. I call it the bonus night, because after that, I never got something like that anymore. You see all these Lyman alpha emitters there. we put a slit here, and we actually discovered that these things are 4 AGN. So this is not only the second largest Lyman alpha nebula, this is also the first quadruple AGN ever discovered. And the two things are coincident. The probability of getting 4 AGN we calculated is 1 over 10 million, coincident with the Lyman alpha nebula, and we have a background quasar here, and we also have absorption statistic of this nebula. So we have everything. That's why I call this nebula the jackpot nebula. It's taking a much longer time to get submitted this paper, but hopefully it will be soon. This time in Science. Let's see if we get it. We also detect other interesting objects from the rest of the quasar. We got a lot of Lyman alpha slugs around fainter quasar than object. You notice that now I don't say Lyman alpha blobs anymore because I think this thing look more like slugs than blobs. So we have a lot of Lyman alpha slugs, and we also have several dark galaxies. I'm showing you one example. This is a very interesting one because it's extended, a very high equivalent width. This is the first extended dark galaxy we have detected. But quickly, let me go to the physical properties of this object. What we can say about the intragalactic medium now that we have seen it in emission. I'm going to show you two cases. A case in which we assume that the gas is mostly neutral, and so the emission is coming from scattering. In order to reproduce the slug, you need a huge DLA, basically, 10 to 21.5, like 20 arcseconds, and a total gas mass of a few times 10 to the 11. If you want to reproduce it with mostly ionized gas, then you still need a very large column density of gas, 10 to the 22. So the slug is so bright that is required a lot of gas mass there in order to be seen with respect to our simulation. Notice that in this case, the column density of H2 depends on the clumping factor because the Lyman alpha emission scales like the density square. So the inferred gas mass is 10 to the 12 solar mass of cold gas in this object. Is there anything like this in the simulations? Well, people that know simulation know already the answer, no. I'm showing here now the column density distribution of a simulation smoothed at the same scale of the observation. We barely go up to 10 to the 21 in column density of gas. There is not enough gas in the simulation to explain what we see in the Lyman alpha nebula. How does it compare with our cases? Well, of course, there's not enough neutral gas, and there's not enough gas if this is ionized and if the clumping factor is 1. The only way in which we can reconcile what we see in the simulation and the slug nebula is to actually assume that we are not resolving a lot of clumps in our simulation. If we increase the clumping factor to a factor of 50 or 100, then we can put these two things in a reasonable agreement. So this is suggesting us that we need more clumps into the IgM. So maybe Avishai can suggest that some VDI also there in the IgM on scales of 500 kiloparsec. And this pretty intriguing because that's actually the same result that we get when we look in absorption around the quasar. And Marie is going to talk about that later, the QPQ program. Also, if you look in absorption, you need this large amount of clumps there. So I just moved to the conclusion then, show you the new technique to illuminate the cosmic gas with the help of quasars. The first results from the flashlight survey, dark galaxy candidates, a lot of gas with high gas consumption rate, compatible with dwarf galaxy, a high redshift, or some part of the metal poor DLA. Silicon galactic medium in emission, compatible with cold streams, 2 large intergalactic filaments. There is some tension with the models, and we need to understand how to put all those clumps there. And the next future, I'm involved in MUSE. You can ask me if you want to know more about that. And MUSE is going to be the ideal instrument to continue this survey in the future around quasar. And then we're also doing spectroscopy H-alpha with MOSFIRE September, October. So a lot of the new things is going to happen. That's just the beginning. So stay tuned. Thank you very much. Yeah, in a sense, there is, because if you just look again at the simulation shown before, you see at least 3 big filaments going around the quasar, while in the observation we just saw 1. This may be actually an indication that the opening angle of the quasar is not 360. And we've been lucky in this case, because in other cases we don't see it around the quasar, that the beam of the quasar is actually getting one of those big filaments around us. So we can explain the sort of asymmetry of the nebula, arguing that the opening angle should be small. But in order to constrain it, we need a large sample of quasars, and that's what we're doing now at the moment.
So, forgive me for not remembering the prehistory of this, but I'm assuming that there are no field, or that the field samples for this have been unsuccessful in terms of finding Lyman-alpha-only emission.
Yes.
Because the small size of those is kind of striking, of the little blobs, not the slug, but the little blob. So if you go to something that isn't a quasar, so maybe like a dense region, some redshift where you have the filter, there were no little blobs found?
No, you really need you really need the brightest quasars in the universe to do that, because it's a question of volume that you are illuminating. If you are close to a faint source, your volume that you're illuminating is very small. So statistically, you don't expect to find any of those.
My question was observational and not theoretical.
Yes,
Okay.
Yeah. So the reason why we went around the most luminous quasars in the universe is to increase the volume that is illuminated. And we detected like 12 objects. So it basically scaled with the luminosity. The reason why we were, few objects in the field may still be this thing. And then from time to time, you see very high equivalent with objects that can be explained just because you don't see the quasar that is there. But the large number that we detected, it's due to the fact that that is one of the brightest quasars in the universe. Thank you.
Okay, let's thank the speaker again.
Evolution of the intragalactic medium. And so today I'm going to focus on 3 particular scales and 3 particular questions on the intragalactic medium, starting from the smaller scales associated with the densest knots, with the densest clumps into the IgM. So the question we'd like to know is, how is gas converted into stars? Is there a dark galaxy phase, a phase in which you have a lot of gas and very little star formation? On the 200 kiloparsec scale, we'd like to know, how do galaxies get their gas? So the circumgalactic medium physics. Is the circumgalactic medium cold, hot, whatever temperature it has? And on larger scales, we would like to know, how do galaxies are linked to each other? What the morphology and the small scale properties of the cosmic web? And in the next 15 minutes, I'm trying to answer these questions if I have time. So the classical approach to study the IgM is in absorption, and we heard a nice talk by Ryan this morning. It's a very powerful method. You get a lot of information about low density gas, including metals, but it has one drawback. Drawback, that is, you only get one-dimensional information on the system you detect. So you get 1D information on Lambda limit system and DLAs, and sometimes it's difficult to argue that a DLA may be a filament, a galaxy, whatever it is. If you really would like to understand the system, you need direct imaging. And my favorite solution to do direct imaging is to use fluorescent Lambda emission. Fluorescent Lambda emission Okay, hi everyone. Thank you very much to the organizing for giving me this opportunity to share with you the latest result from our flash drug survey. The aim of this survey, I'm going to just say it in a few words, is to do direct imaging of the cosmic web using quasar-induced Lyman alpha emission. And it's basically summarized in these cover slides. You can probably recognize this is the cosmic web, that's a simulation, but what you see at the center of the simulation is actually a real image that we took with Keck recently, and that's been featured in Nature recently. And many of my collaborators are actually in this room or in Santa Cruz today. So, but since this is the first talk about intragalactic medium of this Galaxy Workshop, I just want to spend one slide to sort of motivate why studying the intergalactic medium is interesting. And that's one of the reasons that for me the intergalactic medium is very interesting to study, because it provides the link between the bright part of the universe that we can see with the HST optical telescope and the dark side of the universe that we can actually get in our simulation. So if you want to understand how to go from this picture to this picture and vice versa, you have to know you have to know the physics, and it is produced by H1 clouds that are illuminated by an external source, like a quasar or a galaxy. What happens is that the part of the gas is ionized, it recombines, and it produces Lyman-Alpha emission following recombination. So in this case, you can actually detect these objects even if there is no star formation within them, and you can get two-dimensional information. You can maybe not read this from the bottom there. Just want to say that if the gas is fully ionized, the Lyman-Alpha emission is proportional to the density square. So you get information on the density of these systems. So I spent a large part of my career trying to model and understand how bright is fluorescent Lyman-Alpha emission. I'm just going to give you here an example from a recent simulation.